Hello, everyone. We're listening and just sit there. Okay, you can. Okay, okay. So I was thinking that basically we'll have a lunch break and anyway, anyway.
Sorry.
Okay, let me finish it quickly. So this presentation is a little bit I've been giving this presentation for some time, couple of years at least, even more. Okay, so we are trying to develop diamond qubits in our laboratory at Wits School of Physics. So I'm very thankful to people who are working in this project and people at the industry collaboration like Oxford University, Tescan, JAIS, etc., Russian, Mishish, and definitely CSIR, NLC, and NRF. So the thing is that the next slide. Oh, I have to use this one. Just a second. It will go automatically. Okay. Okay, I understand now. Okay, before I start, I must be thankful to people who inspired me to work in carbon system. One of them got Nobel Prize in Physics 2010, and then I visited several places to develop quantum computers. Okay, sorry. Okay, computers, and I had the opportunity to visit NASA to see one of the first quantum annealer D wave, and then I visited extensively Chinese universities, and here you have basically Professor um, from Yale University, whose collaborator got the Nobel Prize, but he didn't get the Nobel Prize. I'm surprised why not. But finally, we have John Martinez. I'm extremely happy to share this photo with you guys. And 2016, I visited his place, and Santa Barbara, I presented talk, and he was very interested in diamond qubits that time. So he's an amazing person, very humble and extremely knowledgeable. So he inspired us to develop something in South Africa, which is not been accomplished yet. However, we managed to buy a dilution fridge and run this system over last 5 years, and we have collected a lot of data at 10 millikelvin temperature and 6 Tesla magnet, etc., etc. So this fridge is ready for qubit installation. God knows when we will get the qubits. Okay, so you know much better than me about qubits, what everybody knows. Even we give honor student this course on qubits. And this is a two-level system, and basically the operation between 0 and 1, you have a matrix basically that changes, and we can rotate the qubits. But the hardware is more complicated. Well, the hardware based on the Josephson junction, and the Josephson junction means if you have two superconductors in between, you can place an insulating layer, and this junction controls the performance of qubits. For example, you can have a flux qubit. We have Josephson junctions, and you can have this current, supercurrent, and this can be controlled by applying gate bias and magnetic field, many other ways. Well, the thing is that the qubit structure is still developing by different manufacturers with different companies, and the technology is not saturated as far as I know. And the tunability of qubits is very important, and that depends on the quality of Josephson junction and whether you can really change the properties of the Josephson junction, whether you can add some spin center at the junction, and you can create some kind of hybrid qubit system, and you can also have inverse Josephson effect, which gives you phase slip qubit. You can think of topological qubit like Microsoft is working on. I don't know the success or failure, but what we believe that diamond is a very strong material, and it can host uh, spin centers, and it can be doped with boron, and it can give you superconducting transition, same as um, aluminium or niobium. It can compete with other superconducting materials. And one interesting thing is that this is a nano diamond. It has a lot of grain boundary regions, and the properties of grain boundaries, actually they can be compared with Josephson junctions. So naturally grown Josephson junctions. So and we have seen some very interesting spin related properties from this kind of diamonds, and we have worked, our student worked last more or less 10 years on this problem, and we claimed some new kind of Josephson junction, also phase slip junction. I'm going to show you in my next slides. Okay, now the last thing is that about diamond, so interesting. You can combine the optical properties of diamond. For example, you can have a nitrogen vacancy center, and you can combine with this Josephson junction, and you can create a hybrid qubit. It has not been materialized yet based on pure diamond samples, but theoretically it has been suggested, and uh, this NV center can be combined with other materials like silicon or niobium Josephson circuits, and they worked quite well. Now, our plan was that we will do everything in one platform, which is diamond. We can create that a structure using this nanotechnology, and we can shape these diamond films and introduce nitrogen centers, and we can create a quantum memory or quantum processor as well. Okay, so here's the thing, in half an hour we cannot explain everything, but I just wanted to say what we believe and what is new in this subject. Well, the first of all, we discovered that unusual superconductivity, I'm sorry, not unusual, unconventional superconductivity, which is spin related. And this is very interesting things. And I communicated with John Martinez, Nobel laureate, and that's the reason I got the invitation to see him. Well, and I many other people basically. And that time paper was not published, but he strongly supported this idea because he is one of the best in the world about Josephson junction. Anyway, this is unconventional superconductor, and very difficult to find an unconventional superconductor and understand the property. And our students were very successful to feed the data, and this kind of peak correspond to vortex binding and unbinding. And this is BKT transition, Berezinski-Kosterlitz-Toulouse transition. And this was this subject received Nobel Prize in 2016, and that's why we were very interested to work in BKT transition in diamond things. Nobody claimed, but we from South Africa claimed this BKT transition in diamond films. And then we have done thorough study of these diamond films, and this is showing one of the, I think the best, the microstructure features of diamond or nano diamond. showing the lattice fringes and the grain boundaries. You can see it was done in collaboration with University of Oxford, and it clearly shows that 45-degree, this kind of angle here, and 72-degree, and that matches with the magnetoresistance, angular magnetoresistance, angle-dependent magnetoresistance. That means we rotate the magnetic field or the sample, and it matches with the microstructure. This is a very important observation we made. It took several years to establish these features and the graphs. Please understand there is no theoretical explanation of high temperature or this kind of unconventional superconductor yet. Well, so it is very difficult to establish these features. So we suggested that this is spin orbit coupling and Rajva spin orbit coupling that is created because of the junction which is electrically charged, and this breaks a translational symmetry, and it gives you basically spin orbit coupling or weak anti-localization effect. Well, we have been working this subject for many years, so it was not difficult for us to suggest this kind of features, and we have seen that DIDV, which is called zero, so differential conductance as a function of voltage, and you can see it can be tuned by changing temperature and magnetic field. Next slide. And this is very valuable information to understand the topological features of a superconductors. And some people called it as a Majorana fermions, but we consider this is a kind of Kondo effect, spin effect, and we still continue research this area like many others. Well, now I'm very happy to show you this kind of oscillations as a function of magnetic field, this oscillation of resistance, and these can be explained by a pi junction. Again, thanks to John Martinez, who identified this as pi junction before this get published. And this opens up a new subject in superconductivity and quantum computers, okay, hardware of quantum computers. So this looks like a phase sleeve junction instead of Josephson tunnel, and you can see like a superconductor, they're separated by a very narrow channel of superconductor, and this matches with our observation, this idea. I'm not going into details. These things are given in many of our publications. How we explain these features R versus T using this quantum phase sleeve junction. But I come to the point which is very interesting. So we are thinking, let's make a circuit, new kind of qubits using diamond. And in the next slide, you can see, okay, next slide, you can see that this is our dilution fridge, and this is NV center. So we are trying to combine these using this kind of diamond circuit. I'm going to show you, and this will create a new kind of qubit architecture. Well, this job is not complete yet. There are several problems in setting up this optical, NV center setup. I mean, we are still learning some parts. Frankly speaking, it will take some more time. But let's go back to the most important feature. So this is it's a piece of diamond. You can see this is the optical image, and you can see the microwave lines, which is created using focused ion beam. And this is a very narrow junction, and this creates a channel, and this works like a phase slip qubits. Okay, so rest of the material is superconductor except this part, which is the phase slip junction. And the size is in micrometer, and it's very small one. I hope you can see it. So this is the first experiment ever. So showed these resonance features, frequency versus phase, S21 and DC bias, and you can see the resonance, and it matches with the DC conductivity measurement. So we can confirm that we have this diamond-based resonator, and we could not really make many samples. It's very difficult and expensive, but we plan to do it in future to combine this circuit with NV centers, and we can run a new experiment. Well, now how many minutes I have? 10? Am I?
Sorry, yes,
okay.
you can complete. Yeah, 10 minutes would be fine.
Okay, great. Okay, so this is the last part of the talk, second and last part of the talk. So here we have been working, since we don't have a quantum computer here, I mean physically. So we depend on IBM what is it, Qiskit or whatever for last 7-8 years, since 2019 basically. So our first student, Farai, excuse me, he was doing a master's with me, actually honors, and then this Declan, he did a third year project with me, and this student worked in as a I think first year or whatever, and the last one is Chisomo is working as a a PhD student, and Shaman Bhattacharyya also worked as second or third year, so I don't remember. Okay. Anyway, so we have been spending time, and they are working on the IBM quantum QE. What is that? Don't remember. The name is changes. And this is the first experiment using diamond NV centers, and the students are very successful in reproducing the experimental data using the NV center. I cannot tell you the details now. It's old story, but the students actually worked with the 3 NV center system, which is very difficult to find experimentally, but they have found the features of the 3 NV center system, and these are the graphs which shows very interesting features basically. Well, and now I can spend 2 minutes on these. So we wanted to see some feature of single NV center. Now this is called the holonomic operation, and to find the geometric phase from the single NV center. Okay, so it is inspired by previous work of some big acquire the geometric phase, etc. Okay. Can you hear me? Hello? Hello?
Yes, yes, I
Okay.
can hear
So
you now.
my office, I think since yesterday I'm finding some problem with the Wits network.
Okay,
Ethernet.
I thought it was me.
Okay. Okay. No more complaint. Okay. And this will match with our previous idea of quantum phase slip qubit, a new kind of qubit. That means a hybrid quantum system. Okay, so here is the thing. You can rotate this qubit, holonomic rotation, or and to collect the geometric phase. And the student know better than me, but I'm trying to explain these things. So here is the thing. It's for a single qubit, and you can use for double qubit system, double qubit holonomic control, and you can use even 3-qubit system. But this is very interesting, the 3-qubit system. It shows the features of a single NV center, and you can have the 8 different levels, and you can have transition between these levels, and using the holonomic control of a 3-qubit system in an NV center, you can record the features, return probability, etc. So imagine if you have many NV centers, so you can have a many qubit system. So and if you connect these things with a diamond qubit system, so you can have multi-qubit system, even in a small quantum chip. That is the idea. Now, I'll spend a few minutes on recent work that student Chisomo it's been successful to develop a quantum neural network using this VQE and many other things, and published a paper this year actually. And this work is continuing with the many qubit system. I'm just skim through these slides quickly. You can see this work in the paper itself. And then he is working, or he submitted a paper on that for simulating diamond 14 NV center Hamiltonian with a proximal 13C isotope. Well, some of the things are written in my book, which was published last year on diamond and qubit system, except the recent one. And these qubits, if we are successful physically to generate the circuit, this qubit will be useful to do better calculation in condensed matter physics, like the geometric phase, which was based on IBM system, but we can do better calculation, and we can have spin orbit coupling. We can do this black hole. We can study black hole. Actually, in fact, we have already studied this SYK model and the black hole simulation of a traversable wormhole. This paper is it's under review. Actually, I received some good comments about the paper, and to explain the oscillation of this return probability. Well, we can explain another time these things. Finally, I come to the most interesting problem. This is ongoing and near future work using IBM QPU. So this is image processing and quantum phase recognition. So Chisomo has already submitted a paper, so I cannot tell details of the paper here. So a quantum convolution network, neural network for quantum enhanced classification of pixelated color images. So using a quantum neural network, so he has reproduced some of the images, etc. This has a great application in biology, quantum computation of the brain, which we have started working recently to look at the real quantum, network, a neural network in our brain, human brain, basically. Okay, so some of the things are you can find in my other book, some hand waving or philosophical idea of human brain. And first, and the most important to acknowledge the student who developed the program. Some of them are not with me now. They are working in different places. but they have good connection with me. Thanks to everyone. And this is me, unfortunately. So trying to recover this dilution freeze and trying to obtain more money for the research. You can see some of my YouTube videos if you like. Actually, this was been asked by this this program. So you can see some of the quantum features videos on my YouTube channel, etc. Thanks for listening to me, and have a nice day. I'm done.
Thank you very much, Prof Somnath. That is very interesting, and I'm sure that people will be visiting your YouTube channel to learn more.
Thank you very much. That will be more than enough.
It was.
Just
It was more
subscribe,
than enough.
subscribe my channel. Nothing else. I'm not looking for money, funding, etc. Subscribe my channel. That's it.
Yes.
Yes.
But yes, but very interesting. Can I ask a quick question? The diamond, you talk about diamond nanowires. What does that mean? I mean, it is the element, I mean, it is the mineral, diamond, right? Or
Yes,
is it
it's a semiconductor insulator. Okay. So
right, right.
you can cut the diamond and you can create okay. Here, you can cut the diamond using a machine, focused ion beam, which I'm not showing here because of the time limit. And do you see the size? Is that this is 0 point? Actually, this is 20 nanometer, something like that.
Right. Huh.
Yes. This may not be 20 nanometer, but 30 nanometer. But I have another picture which shows 20 nanometer.
Right.
We cannot go less than 20 nanometer, difficult, it will break. But
Okay.
you need this kind of thickness. So this will be used as the phase slip junction. That means it will stop the current, and by adjusting this size, you can control the super current in this in the loop. In this loop.
Okay. Right. So obviously this depends on the molecular structure of diamond that gives you these properties.
Diamond molecular structure is it's a very good question, maybe very deep rooted question. Anyway, so actually, what you see in the textbook, diamond is a cubic structure. I mean, diamond structure. But if you go to nanoscale here,
Yes.
it is very uncharted territory. I mean, it can be SP2 type, it can be SP3 type. It's still people are doing research, and this research will
Oh,
be continuing. What is the exact molecular structure of diamond at the nanoscale? That's a very good question.
right, right,
And
right.
our student, another student, Venkatesh, okay, he published a paper recently. Actually, it was published last week, about the molecular structure of diamond here at the grain boundary. So it's very, very complicated. You can read, it is described more details in my book. I address this point. So we wanted to break the concept of crystallinity in diamond, because it's a mixed phase. It's hybrid structure anyway.
Yeah.
If it is a pure crystal, one type, it cannot be superconductor. So you have to have a defect. You have to introduce defect and special molecular structure, and that becomes superconductor.
I see.
That particular thing is very important, not the whole structure.
Right, right.
Like this part is most important, not this other part. Only
Yeah,
this part is
yeah.
important.
Right, right.
Yes.
Fascinating, Prof. Thank you very much indeed for your talk. Let me see if there are questions. There's an open question from Kenneth. Is the diamond synthetic, and can you reorganize or manipulate its properties to achieve improved or the desired performance?
This is very good question. Okay, Kenneth, I know him very well. Okay, I think, yes, this is synthetic. This is lab-grown diamond. I mean, we have grown the diamond, some of the diamonds in our lab. We have a setup for diamond, microwave CVD. However, for good quality diamond, we cannot grow in our lab. So we have to buy or get it from the bigger system. The quality matters. It is really important how good your diamonds are. Good means not a pure phase, but how you control the property of diamond. So we have been working last 20 years on diamond synthesis. Maybe more than that, maybe 25 years. Okay, I'm not that young. Anyway, so we know in and out of diamond, not superconductivity only, but semiconducting properties and growth mechanism, etc. So that inspired her to work in diamond-based qubits. It's a very difficult job, although. For
I'm sure.
example, you cannot control the NV center's position in diamond. It's very difficult. It's still open problem. Yes.
Interesting. Gosh.
It's interesting. That's the reason we are in South Africa. And if we say diamond things, everybody gets interested all over the world. You are from South Africa. That means you have some interesting piece of diamond.
We know about diamonds in South Africa.
I sell that point, and sometimes I lie that okay, it is from one of our special diamond from South Africa. But these diamonds we use, basically these are lab grown.
Okay. Well, we're good at that as well. Yes.
It's interesting.
Well, I'm very envious that you've met all these people on your photographs there, and particularly John Martinez.
There are many more, but I just put the recent ones. No, the selected ones. Okay.
And you have the blessing of John Martinez, so it must go well.
I had little contact with him. The main problem is that he had a problem. He wanted to come to South Africa, basically in 2017, but he had a problem with Google itself. I mean, he had to leave Google, and he could not really communicate with people, basically, because of the security or whatever. They have some restrictions.
My goodness.
So
that
you
is
cannot reach him
interesting.
easily. I mean, it's very difficult. But you cannot believe such a nice person. I mean, you cannot find this kind of person very easily. So
Yes.
down, so knowledgeable. So he fetched me from my hotel, and probably he paid for the hotel also. I don't remember. Anyway, that's not an important thing. He fetched from my hotel and dropped me off, and the whole day, 2 days, actually spending time, and incredible. That kind of
amazing.
Well, I met few Nobel laureates like here. He's good friend of mine. I still have very good contact. He's in Singapore right now. But knowledge-wise, John Martinez, you cannot believe the knowledge. It's not just luck. He got the Nobel Prize. He deserved it. You cannot believe that person is so knowledgeable and so down to earth.
So interesting. Oh,
It's a lifetime opportunity.
Yes.
Okay. If we can establish any quantum in our life, I will go and grab him to come with me to inaugurate this program. That I will do first thing. That is
get him to come and work in South
anywhere
Africa.
in the world, if I get money and he can,
Yeah.
if I can establish a quantum computer, superconducting, the first job is to find him and
I wish you all the luck in the world.
Yes.
Wonderful.
In fact, I will invite all of them, basically.
Yes.
Don't worry. God is listening to me, and sometime it will happen.
I'm watching the space.
Thanks for recording my message or my voice. Yes. Okay.
Thank you,
No
Prof
more.
Somnath.
No more. That's enough for today.
Okay. Thank you.
Nice talking to you. Thank you very much. Okay.
Okay, can I give our remaining speakers who are still with us a chance to say a word or two? Mervyn, Christopher, I see you still there. Would you like to say some last words for this
To
gathering, for
me,
this discussion forum?
oh, okay. Let me.
Mervyn, I think Mervyn has gone to have coffee.
Oh no.
Okay, Dr.
I will
Isaac
tell
Melchick.
Marvin. I will tell him in person.
Okay,
He's good friend of mine. Hmm.
good. Um,
He supports us
Hi,
also.
can you hear me?
Anyway, so I
yes.
can stop.
Okay.
I just want to thank you for having this platform and allowing us to share some of the good science that we're doing. And what's great is it's more than science, right? Everyone's trying to turn this into technologies that might impact lives. So yeah, thank you so much for doing this.
Oh, what do I
Thank
do?
you very much, Isaac. I really appreciate that you participated today. It's an honor to have you all. And yes, I think it's not often that we have discussion forums where there is so much hard science to be that is presented and that the audience has to grapple with. And I hope they weren't discouraged by it, You will take from this discussion forum what you have been able to absorb and process, and that is, even that is important. You can also go back to the presentations and the slideshows on the NSDF website, and I urge you to do that because this is really valuable knowledge. Nuri, Mohammed, do you have some last words for us?
I just wanted to say thank you for the opportunity to present on the quantum impacts on cryptography. While I did not cover the heavy science and physics, I aim to translate quantum into its real world technology and the security implications for everyone, including us as individuals. And thanks again for the opportunity. Really
That's
appreciate it.
exactly what we were hoping was going to happen. Thank you so much.
Thanks.
Anyone from the audience who wants to say something, please raise your hand. I see Harde Schreiling is there. See some other people I recognize. Jody Watson, who was addressed us yesterday. Jody, would you like to say a few words again? Yes. You may unmute yourself. There you go.
Thank you so much for having us over the last 2 days and for putting this all together. I think it was really insightful, and a lot of the conversations, I think, explored a lot of different topics. And I hope that it's given people a touch into what quantum science and technology can do in the future and what we are doing now. And if you have any questions, I know that a lot of the researchers and speakers are very willing to help people understand more, and you can always reach out to SAQT as well.
Fantastic. And with that, I want to thank SAQT very much for this collaboration in putting this together today. It really has been incredibly valuable because you bring the expertise that is necessary to discuss any of this. Yes, Harde Schreiling. There we go. You can unmute yourself.
Hi, Yancy. Yeah, thank you. Sorry, I was just in the passage when I heard you. I was actually going to finish.
Sorry, I caught you out.
So yeah, I actually sat through both days, so it was really very interesting. It was also very encouraging to see a lot of the work that has been reported over the last 2 days actually was work that was born in the CSR's rental pool program.
Yeah.
Some of these projects are actually still continuing under the banner of the rental pool as well. So yeah, it's very good to see this, and I wish all my colleagues who've been doing such excellent work lots of success and bringing this to the market, because I think that's very important to see at the end of the day. But yeah, thank you so much. It was a great opportunity to hear what everyone is doing, specifically also to see the context of QT. So it was very encouraging. Thank you so much.
Fantastic. Thank you, Hardus. Thank you for responding. This is indeed a long time coming. Lots of work that has been done at the CSIR and at universities, and that has been largely invisible. So I'm very pleased that we were able to host this discussion forum together with QT. Yes, Isaac Napi says, thanks, Hardus. Wouldn't be possible without the energy you invest in us and our research. Great. All right, on a final note, please look out for the NSTF South 32 Awards call for nominations. We're kicking off the next round of the awards, and there's some great news involved. In that, we've introduced a new award for research software. So research software that has allowed researchers to do their work, because it depends so much on computers and software nowadays. You can't, as many people have, speakers at this forum have said, you can't actually do anything without that. So we will be we're hoping that the software developers come out of the woodwork and participate in the nominations for the NSTF Awards. We have 2 awards. The one is for any scientific field, including humanities and social sciences. And the second one is for human language technologies. We're doing it in collaboration with SADiLaR, which is the South African Centre for Digital Language Resources. So that is a very exciting development. I feel like we are finally catching up with what is happening in the country, because wonderful work is happening behind the scenes that is largely unknown, not public and invisible, and often not receiving recognition. Okay. Vilna says, thank you for affording NSTF the honor of your participation in the discussion forum. Help us spread the word and share the outcomes as widely as possible. Indeed. On that note, I want to thank you all for attending and for staying the course. We've got 38 participants at the moment, and I think that is very impressive at 10 to 2. It has been a very full 2 days, very rich content, and often quite difficult to grapple with it while listening. So I'm sure some of us will be going back and seeing if we can get more knowledge out of it when we look at the presentations afterwards. Thanks for your attendance, and have a good day further. Goodbye.